So last time we talked about Kepler's laws because we're going to use logarithms to show the relationship between the orbital period and the distance of solar system objects. So just as a review, Kepler's laws is the first law is that all orbits are ellipses. Second law is that a line joining the planet and a star sweeps out equal amounts of area in equal times. That's basically a way of saying that the planet moves slowly when it's far and fast when it's close to make that shaded green area equal area. And then here's third law. Here's what we're going to be looking at. So the square of the orbital period of the planet is proportional to the cube of the semi-major axis. It's essentially the radius for an ellipse. And if you plot the cube of the semi-major axis against the square of the orbital period, all objects in the solar system line up in a straight line like this. And this is using a log scale on x and y. So we're going to use log to show this. We're going to actually make a chart like this in Desmos, and here's how we're going to do it. So we're going to go to Desmos, and I'm going to make a graph. So please go to Desmos right now. You should be in Desmos. When you first go to Desmos, you click on Math Tools and Graphing Calculator. So you should be doing this as you go. I should see everybody's Desmos up and ready to go. Over here in the equation area, you should click on the plus button and make a table. So we're going to make a table, and instead of x and y, we're going to be graphing the distance. So if you click on x and you delete x, so you can type d, and then our units are going to be astronomical units. Does anyone remember what an astronomical unit is? AU. It's the average distance of the Earth to the Sun is a measure for solar system type distances. So I'm gonna type D and then underscore. That's shift minus, and then capital AU. So that's distance in AU. Yeah, and then shift for underscores. So if you're just doing x1, you can just type x and then type 1, and it does the subscript for you. But if you want to do different subscripts, then you can do the underscore key. And the next one is going to be the period in years. So I do lowercase p, and then underscore, and then YR. That gives me a different variable here. And then I'm going to go and look up astronomical data. So my first row is going to be for Mercury, and then Venus, and then Earth. So does everybody know the acronym to remember the memory key to know the order of the planets?
My mother kills. My very.
My mother.
There's no planet K, so probably kills is not one of them.
My very extravagant mother. This is harder to
Jubilantly.
No.
Jubilantly.
Just served us noodles.
No. Pancakes.
So the way I do it is my very earthly mother just served us 9 pizzas.
Oh, okay, yeah.
9 pizzas, and for Neptune.
I got it most of the way.
So we're going to go get astronomical data. So I'm going to go. I chose to go to the Royal Museums at Greenwich, and if you search for solar system data, they've got a table of solar system info, solar system data. So this period is once you get far enough out, Miles.
Yes.
It reports the year in years. But if it's less than a couple of years, like once it gets to Jupiter, almost 12 years, it's reporting it in years. So Mercury, Venus, Earth, and Mars is reporting it in days. So we'll have to figure that one out. Also, distance measured in astronomical units. They show the perihelion and aphelion. That's the closest point and the farthest point. So we're just going to combine these data and just average them.
I've never heard those used. I always thought it was like apoapsis and periapsis, right?
In
Those
general,
are the same.
in general,
Yeah.
yeah. So So helion, what is the suffix helion refer to? So helios is Greek for the sun. So perihelion is close to the sun. Aphelion is the farthest point from the sun. So the Earth, so the moon has a perigee and an apogee. So that's closest point to the Earth and farthest point from the Earth. The planets have a perihelion and aphelion. So
What would actually it doesn't really matter.
so we're going to combine these figures just by averaging them, and we're going to convert days into years. So we can go back to Desmos, and we can start filling in our table. So the first one is going to be for Mercury. So let's start putting in the data for Mercury. So which one do we want here for D and which one do we want for P?
For D is the average.
We want to average. So I'm going to click on parentheses, open parentheses, because I'm going to divide by 2. I'm going to say 0.31 plus 0.47, close parentheses, divide by 2. And I don't have to do anything else. Desmos can do this calculation for me and give me the distance.
Should we go ahead and do the rest of them too?
Yeah, so you can actually, with your mouse, you can highlight this, press Command C, and paste, and paste, and paste, and paste, and paste. We want 9 rows. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and then I'm just going to put in my other data. So you start doing that, and I'll do it at the same time. For Venus is 0.72, average with 0.73.
How do you paste? Yeah.
So on a Mac, it's Command C and Command V. On Windows, it's Control C and Control V for copy and paste. So highlight it first. So take your mouse and highlight. Are you on a Mac or Windows?
Mac.
So watch what I'm doing here. Watch up the screen. I'm highlighting this first, and then I hold down Command and press C to copy, and then I come down to my blank area and I do Command V to paste.
Okay.
So keep going all the way down the table.
How many do we need?
It's 9 rows.
Okay.
So we're including Pluto because we are Team Pluto as a planet.
Let's go, Pluto. Woo.
It's alright.
Okay, that's nice.
So you want to carefully check that your data going into your table is accurate, because if you put in faulty data, have you heard the expression garbage in, garbage out? Garbage in, garbage out is an expression from computer science where whatever your calculations are, whatever your program is, if you put in nonsense data, the result might be nonsense.
How did you paste and everything's different?
I'm making it different. It's
Oh,
as I was pasting it, it was all the same.
And then what do you want us to do for years?
So for the actual years, so for Jupiter you can put in 11.86. For Saturn you can put in 29.46. But we can start at the top together. We're going to convert this to years. So I want you to think about how we can convert a data in years, that's giving in days. What?
Divide by 365.25.
Well, see the figure here for Earth's year, 365.26. Let's use that for our conversion to years. .28, 20.09. Neptune is 29.80 and 30.32.
What is Pluto's?
What do you want
Okay, so for Pluto, I'm gonna go to Wolfram Alpha.
What do we round up to? Like
You don't round.
Data disappeared.
You don't round. You just
for years.
don't round.
So exactly.
So for in Wolfram Alpha, I'm gonna say Pluto orbital period and distance to the sun. So orbital period is 249 years. So your last
But could you
column here, you can for period you can do 249, and for distance you can just put in that figure of 35.24. Can I scroll what?
Can you look up just Pluto orbital period real fast? I want to see if you're getting the same thing as me. I'm getting something weird. And then scroll down just a little bit. So get the first comparison as time.
Comparison is time.
What?
I can't see the other one.
Is that what you had me do?
Yeah.
Nice. Thanks. That's on the recording. Appreciate you.
Alright,
all right,
I
so-
gotta watch it over and
So what are we gonna do here for Mercury's period? How are we gonna calculate Mercury's period? And the unit we're using here is years.
Well, you're gonna do that divided by 365.26.
The figure here in the table, so it's 87.97 divided by 365.26 days per year, and that gives us a figure in years. So I'm going to copy this as well. So Venus is given in days, Earth is given in days, and Mars is given in days, even though it's more than 365. So Venus is 224.7 days. Earth is, I could just say 1 because it's going to be 365 divided by 365. And then Mars is going to be 686.98. After that, I'm just given in years, so I can do 11.86 for Jupiter, 29.46 for Saturn, 84.01 for Uranus, and 164.79. I heard that, Snigger. Did you know that NASA found a ring around Uranus? Sorry, I teach high school.
Oh my god.
You should start teaching elementary school.
So,
Oh no.
They find
Oh,
it.
Dad.
I know it'd be much.
so Desmos starts graphing this for me, but it's just on a linear scale. So as I zoom out, I can zoom really far out and see all my points, but you have to zoom so far out that you can't really see the closer in rocky planets. And if you zoom in far enough to see the rocky planets, the other planets go off the scale. So here's your data. Are you guys done with the data?
No, wait.
Yes.
Okay,
It's
we'll
almost a perfect
we'll wait.
quadratic.
I'll fast forward in the video.
Sorry. Okay, I'm done.
I just
Oh my god, that's a big jump. That's an even bigger jump. Oh, and that's even bigger. Oh. Hi, Pluto.
Look at how close these points
Hey there, Pluto.
Why are
So do you see the period? You see Pluto's orbital period? 249 years. Do you know that Pluto has not yet made one orbit around the sun since it was discovered?
crazy because it was discovered in the 1800s.
Oh, this one's better.
All right. So I have a bunch of data points on here,
I got it.
but I would like to label these. So Desmos doesn't let you add a column and just put a label. That would be probably a nice improvement if they could do that. So what I'm going to do here is I'm going to do a little trick. I'm going to reference the data in my column just by their position in this data table. First thing I'm going to do is I'm going to set up a variable a, and that's going to be my distance in AU. So D underscore capital AU. And I know that that's working because I've got a 9-element list here. I can click on it if I want to see all the elements. I'm going to call B. B is going to be my period underscore YR. And this allows me to make a ordered pair point. So the first one is going to be A at offset 1. This is just referring to the first item in the list. I've renamed my column here as A, and then I'm going to say A at offset 1. So parentheses A bracket 1 gives me the first item, and then B bracket 1 gives me the second item. And if I click on label, you see that it puts that data point out here next to my first point. But I'm gonna actually type in this field here, and I'm gonna say this is Mercury.
So when I put in the B equals PYR, it added a line.
Do lowercase b.
It is lowercase. But
So if you misspell this at all, it might give you a line. So P, or if you do uppercase P sub YR, it doesn't know what that is, so it's just thinking that it's like giving you a starter line. But if I do lowercase p underscore YR, exactly as I spelled it up here in my table, then that's giving me a convenient name for that column. So this is now column A and column B.
I had to do it opposite because I put capital P.
Right. So you have to spell it the same is the point. So now I'm going to use copy and paste again. So I'm going to copy this, come down here, paste it in, and change it to A1 B1. Sorry, A2 B2. And I'm going to call it. What's the next planet after Mercury?
Venus.
My very Venus. Paste again. A3 B3. Label my very earthy. Paste again all the way down to 9. So we want A1 B1 up through A9 B9. Mother Mars.
Mr. Shale, do you think we'll ever live on Mars?
I wouldn't want to. Mars doesn't have a liquid core, so it doesn't have a strong magnetic field. So even though it's farther away from the sun, you see how much farther? This is a linear scale. So this is how close Mercury is to the sun. This is how close Venus is to Earth. This is how much farther Mars is.
So why can't we?
So it's farther from the sun, from the sun compared to the Earth, but it has a weak magnetic field, so it doesn't protect you from harmful solar radiation. So Venus is a hot house, is a gas. What is it called? Greenhouse. Runaway greenhouse effect on Venus. So you pretty much cannot survive on Venus because of the enormous heat and pressure there. My very earthy mother, just Jupiter. 6, 7, 8, 9. 6.
What's S?
Saturn.
Oh.
7. 8. 9. My very earthy mother just served Saturn. Us, Uranus. 9, Neptune. Pizza's Pluto. All right. right, so by labeling, so this ordered pair allows me to add a label, and then I can give it an actual name instead of just the data points. But here again, this is a linear scale. So if as I zoom out, I can see, or if I zoom in enough to see the rocky planets, I can't see the gas giants. If I zoom out enough to see everything, then the rocky planets get crammed into the corner, and I can't really see any data from them. So I'm going to, instead of doing a linear scale, I'm going to change to a log scale. Log scale.
It's not.
You guys.
Must have wrote something.
It must be.
I don't see what's wrong with it.
It must be trash.
It's all.
It's algebra.
So the way I'm going to do this is I'm going to convert all of these to the log equivalents. I'm going to change these to log. And the way I'm going to do that is I'm going to click down here in an empty line, and I'm going to add a new table. And then I'm just going to change this to, instead of DAU, I'm going to say LN D sub AU, and then that completely fills in the table for me with the log equivalents. And then here, instead of PYR, I'm going to say LN lowercase p underscore YR.
Oh wow. Oh, that's cool.
It gives me,
Yours is actually really weird. Instead of doing like the like it has the
Earth is negative.
warning, like the that triangle that says you can't do this.
yeah.
I don't see what's wrong with it.
Can you bring that up here, Emily?
Just put LN instead of X. Do everything that's different. And then go down to AU. Both capital.
You see how DAU gives you a 9-element list and PYR does not? And it gives you a line?
Yeah.
That's because it doesn't know what PYR is. Maybe you called it capital P when in the data table it says lowercase p, or vice versa.
I would.
Same thing.
Yeah.
Where's your data?
It's these. It's in a table, but it's,
Where's the table?
I don't know. It showed the table. Then I changed the scale in the settings here, and then
I
it
bet you
stopped
were not
being in
about
the
to say
table.
that.
No, I wasn't.
You deleted your table somehow.
Okay.
So hit undo, Command Z until it came back.
Anyways,
No, it's
what did I do?
Okay.
Nothing.
Thank you.
hmm
Nice job.
Any luck, Emily?
Why is
Okay, so
Wait, can you hang on for a second?
you want to show me?
Pluto's period, like, if you do everything, it's what makes it weird.
Pluto, no, this is
mathematically.
Is your graph working so far?
Yeah.
Okay, so now I have my my log scale. I have my log scale data points all here and lined up, but my labels are still on my linear data. So I'm gonna update them by saying, instead of A equals DAU, I'm gonna just click in here and put LN. So A equals LN DAU and B equals LN PYR. And I'm gonna click on my data here, my first data table, and unclick those points because I don't need them anymore. So now if I zoom in, I've got a nice linear
Except for
array
Pluto.
of all of my.
Pluto's
Okay, so basically
Except for Pluto.
Whoa. Yeah.
So
Pluto's different.
no discrimination.
so now I'm gonna click on Emily. You still having trouble?
No, I'm helping her with that.
So I'm going to use Desmos to calculate a linear regression of this line. So to do that, I'm gonna come over here left of my log data table, not my first data table, but my log data table, and I'm gonna click on this. This button is add regression.
What?
So over here to the left of my data table, there was a button called add regression.
Ah,
Oh yeah, I see it.
How did you? What?
My
What can this
regression's
do
a
to the
little
log
off.
version? Like,
What?
what can the log version of the graph tell you?
So the problem. So let me unclick the data points. Let me unclick all of my. Well, no, I won't unclick them. I'll change them back to linear. So I'm going to get rid of the log here, and I'm going to get rid of the log here. So first of all, and let me get rid of my line for my linear regression, and now I'm back to my log scale. I mean my linear scale. So the problem with this is, what's the relationship? I mean, is it linear?
No, it's
No.
exponential.
It might be exponential.
Also,
Um,
no,
but-
Pluto.
But if I zoom all the way out, I can't see the first data item. So on this kind of chart where things start growing exponentially, I can get that under control by just applying log to both scales. So this is a little bit unorderly, but then if I do the instead of showing the points as the XY data of the distance and the period, I do the log of the XY data. So that this gets it, this changes it to a linear scale, from linear to log scale. And then I can find out something about what the relationship is by doing a linear regression. So
Wait, what do you press to get that?
linear regression, over here to the left of the log table was a little button.
Oh, okay, that.
So click on that button, that's add regression, and that calculates my line of best fit.
oh, okay.
And then as Miles keeps wanting to point out, Pluto is not super on that line of best fit. It's pretty close. It's not on the line. Neptune is a little off too.
Pluto matters.
Can we kill it?
The line is not.
You're gonna send another dart mission to it?
You did a linear regression on your
There,
linear
you do a
data.
Power regression on your linear data. It has no R squared of 1. And then
You want to do a linear regression on your log data. We added another table here and made the columns LN, DAU, and LNPYR.
It doesn't let me do that. It doesn't let me add LN.
We're just saying similar things as well.
So add
Now
a
you're trying to
table.
make him say it too.
Oh, and copy all the data.
No,
What am I
don't have to
trying
copy the
make
data.
say?
So I'm going to say natural log of
Just me, or is it
D
giving you hand
sub
I'm sorry.
AU. What did you call
Is
it?
it
D
school
sub
street?
capital A little u.
Is this
And
agent
same thing here,
You're
ln of PYR.
right.
So,
Why
right,
is
R.
Why is?
What did you call it? Is that capital P?
oh
Yeah.
Oh wait.
So you make it harder on yourself if you don't do it systematically. So this is a little d. This might as well be a little p. We did the AU in all caps because astronomical unit is in all caps.
Is this giving
So if you're more systematic, you can avoid those kind of errors that are for nothing. And then this is the linear regression that you want to do here on this log table.
Thank you.
So for this assignment, this is the screenshot that I want. So I want the log table, I want the linear regression, and I want your graph showing Mercury through Pluto, and the line of best fit. If the colors are different from mine, it doesn't matter at all.
Why is your Pluto so close?
So Pluto is not that far. So this is a log scale. This is first of all, this is a log scale. Pluto is plenty far from Neptune, but on a logarithmic scale, it's not.
well, Okay.
Yeah,
mean-
he put his by the natural log. Like he put it of natural log of like the rate of change.
Right. So I changed renaming the data columns.
Yeah.
It started off as being the linear data, A equals DAU. That's when it gave like the exponential distribution of the planets. I changed it. Now A and B are the log versions of that, and that updated all of my points. So my named and labeled planets got rearranged, and I did my linear regression on the log data. So this is what your screenshot should look like. Include the log data table, include the linear regression, and include your chart showing Mercury through Pluto with the line of best fit. Take a screenshot and you can upload it, and that homework is done. I have one more thing that I want to show you about this, but this is what you need for this assignment.
So do we just take a pic of this?
Is as long as you're including your log data table, linear regression, and the entire chart, all the planets and dwarf planets, then yes, that's all I need.
Miles are
Like,
Kepler's. This is Kepler's third law.
so like if I took a screenshot of this, would this be good?
Can you scroll? You see how my linear regression shows my my Y and my R?
Yeah. Okay.
What?
Like this?
Why are your planets
Is it the
closer?
Kepler law assignment?
What were you saying?
Yeah. Yeah.
I don't know what you said.
This is good though, right?
No.
Yeah.
I got it.
I got it.
I'll take a screenshot of this.
You said so. Pluto's actual distance was 35.24. There's no reason to divide that by 2. We're dividing all these by 2 because we were averaging 2 figures.
Okay.
We just have.
Oh.
We looked up on Wolfram Alpha. It just gave us 1 figure for the distance for Pluto. It should not be divided by 2.
But I feel like your other planets are also closer. Will that change? I see.
So having one data point be off, that changes your line of best fit. Okay, all good for that?
And we need the LN.
Kepler's third law.
Kepler's third law is the name of the assignment. And then I need you to, on your notes, I'd like for you to please write down the equation for the line of best fit.
Wait, what?
Write down the equation for the line of best fit.
The one on this one.
Yeah, the linear regression did it for us, but I want you to write down that equation
On paper?
on notes, on your notes.
And then do you want us to take a picture of that?
No. This screenshot that I described, that's the entirety of the Kepler's third law assignment.
So the line of regression is the y equals 1.517 thing.
Yes.
Can you return mine really quick? I accidentally uploaded the wrong thing and forgot to check.
I can't do it right now because I'm recording this lesson for the other class,
Okay.
but I can do it.
Okay. Thank you.
Remember when I put it in your bag and zipped it up?
No, I don't.
Oh, here, I'll do it again so you remember.
Wait, so the linear regression
You're so bad.
equation
Why is your potato
that's
not-
on like in the LN table,
Okay, that
that's
was
underneath the linear regression.
So where it says linear regression right here,
Yeah.
you're going to copy down this equation for this line. This is the equation of this red line.
What would you call this line?
This is the line of best fit or linear regression.
No, like for my notes, like what would I call this line going through?
This is Kepler's third law, linear regression, or Kepler's third law, line of best fit. Yeah, his list of laws. Yeah, the three laws.
I can't believe
Do you know what they are? What's Kepler's first law?
The one about rotation of Earth, or of rotation of planets around a star.
Isn't
Is
that-
what?
I think that was the second one, right?
It's
No,
like
It's always
The
equal
same.
given the same amount of time.
it's
No, that's
the
the second
sun
one.
is the focal point of
The sun. The sun is at one focus. of
an
the-
ellipse
of an
that is
ellipse.
the planet's orbit.
The planet's orbit is an ellipse with the sun in one focus. That's Kepler's first law. What's Kepler's second law?
A planet covers the same area.
And given the same amount of time.
A line connecting the planet and the sun sweeps out the same area in the same amount of time. That's Kepler's second law. What's Kepler's third law?
That the planet's orbital period is proportional to the size of its orbit.
So it's actually, so this is why we used log, because it's the cube of the orbital period is proportional to the square of the distance.
Is that one of the reasons Pluto isn't a planet? Because it screws up the linear regression.
So you know what? If we took out Pluto,
It would be a perfect fit.
it would be
It would be-
okay. So I wrote this down on my notes to talk about separately. But do you notice the r squared and the r?
Yes.
So these are figures from statistics, and you'll figure out how to calculate this separately. So Wolfram Alpha and Desmos calculate this for you and just give it to you. But these are measures of how well the data fits. Yeah, so the linear regression, the closer you are to 1, the better the fit. So look how good this fit is. So r squared is 0.9996, r is 0.9998. But let's get rid of the data for Pluto. Let's get rid of this line, this whole row.
It would be 1.
We get rid of the
Wait, actually?
we get rid of
Very,
it,
very close.
and then the notation for Pluto went away because it doesn't know what there's no a sub 9 anymore. It's undefined. Doesn't know what that is. So so there's 1, 2, 3, 4, 5, 6, 7, 8. So this is okay. And also let's write down this
That's why.
line line of best fit. So write this down because we're going to compare. Okay. Can I switch over to notes? Can I take the graph off the screen?
It also, if you do without the log, it has a cubic regression and a power regression that's perfect. But Pluto screws it all up. Is that why Pluto isn't a planet?
That could be why, actually.
They just
So you can probably tell graphically if there are any problematic planets, and I don't see anything. I don't see any obvious outliers. So all the way Mercury, Mercury with an R.
So if you see residuals, scroll down to the bottom. If you plot the residuals, then it will show you how far off each one is. So that the blue dots on your graph now show how far off each one is, and there's in your table a second blue dot plot, which tells you exactly how much each one is off. from
So
each
Venus is off quite a bit,
So,
and then
look at it like
Mars, Earth,
sometimes-
Mars,
sometimes
Jupiter.
it'll say like 9.7
Saturn.
times 10 to the minus 12.
Oh, I see.
Well, how do you
Oh no, this is tiny. This is times 10 to the minus 4. So these variations are tiny.
And the blue dots tell you graphically.
Mr. Shadle.
But there's nothing that's even close to a tenth. There's nothing even close to 1%. So this is 0.1%, 0.1%, 0.5%, and these are tiny numbers. So it's a very good fit, and R squared come out to 1. So this is pretty much as good as you can get, even with realistic real life data, accurate data of planets and orbits and periods.
I found out
I
why
mean,
Pluto is not a
distances. There's a few reasons.
Yeah.
I don't want to talk about that.
planet. No, but I.
So let's go to notes.
Too much.
It meets. It
Let's
meets
go to
two
notes.
of the criteria.
It's too close to home.
It meets two of the criteria.
I don't want to talk about that. So this is including Pluto, and this is excluding Pluto. And here r squared was 1, and r was 1. So this is a very good fit. If it was a perfect fit, what would we expect our equation to be? If it was a perfect fit. So I've got some little bit of noise in the data, or a little bit of inaccuracy. So if we're not ready to answer that question yet, let's look at the original equation. So if you recall, Kepler's third law said what?
Sorry, can you state that again?
So what was Kepler's third law?
That
Uh,
the orbital.
orbital period corresponds to the cube of the cylinder graph.
So P
This
is proportional?
the square.
P squared is proportional. P squared is proportional. So Kepler did not write this law in terms of logs. He wrote it in terms of linear data. So as you notice, that swoop of our raw data was exponential. It was exponential. So the way Kepler's third law is usually expressed is P squared equals A cubed. So the relationship is usually written as P squared is proportional to A cubed, where P is the orbital period and A is the semi-major axis. And did we talk about semi-major axis last time? So if you have a circle, it has a center and a radius. If you have an ellipse, it has two foci. That's kind of analogous to it's like the center but doing double duty, let's say. And it has a major axis and it has a minor axis, and the semi-major axis is the center to the end. So this functions kind of like a radius for an ellipse. It's analogous to a radius. So this is the distance. This is the average distance. Average distance
What is that fish thing?
to the star. To the star or to the sun or to the planet. What?
What is that fish thing between P and A?
So the fish thingy means is proportional to. So how do you upgrade from a proportional statement to an equality? What do you need?
Another like an X,
What do we call it?
variable.
No.
What? A constant
Of what? And what is this thing? This means it's proportional to?
of the two.
Constant of.
Two.
How do I go from proportionality to equality?
Variation.
No.
What?
This means it's proportional to. Somebody must remember this term.
Yes.
Lily, what's this term?
It's proportional.
Yes. This means it's proportional to,
Yeah.
but to change to go from proportionality to equality, I need what? A constant of proportionality. Proportionality. But that's normally the case. But if I say orbital period is in years and semi-major axis is in astronomical units, my constant of proportionality is 1. So I get this for free. I don't have, well, I mean, technically I do have a constant of proportionality. It's 1, but I can just write this proportional relationship as an equality as long as I use orbital period in years and semi-major axis in astronomical units. So let's take our p squared equals a cubed, and let's apply log to it. Let's apply log to both sides. So who can help me with that?
Apply log. Oh. 2 log of p, right?
One step at a time.
Sorry.
One step at a time.
So
How do I apply log to both sides?
log of p squared.
So I'm going to use natural log,
Yeah.
just for no reason. I just want to. I could use log base 10 if I wanted. ln of
p squared
equals
ln
ln
a
a
cubed.
cubed. Okay, and now you're going to use power property, it sounded like. You were going to use power property?
Yeah. And so I just move them both to the front, so it's 2 ln p
2 ln p,
equals
3
3 ln a.
ln a. And this is on my y-axis. This is my x-axis. So could I write an equation with a slope? So what's the general equation for a line?
Y equals plus
Okay, so I want this in that form. So ln p serves as my y,
okay, so ln p equals
and ln a serves as my x.
m
It's going to be m,
ln
but what is it in this case?
a. Oh, 3 ln a plus 2.
Am I subtracting 2 from both sides to get rid of this 2?
Yeah.
Yes.
No, it's not a plus 2, so I'm not subtracting 2.
You're
You're
dividing.
dividing it.
Oh.
I'm dividing both sides by 2.
So it's all divided by 2, right?
So what do I have on the right side?
ln p. Or right now.
Left side is ln p, right side is
3 ln
3
divided by 2.
over ln a.
3 halves ln
right.
3 halves.
So what is m in this case and what is b in this case?
a. M is 3 halves.
3 halves, and b is what? Miles?
B is the, what's it called, 1
It's 1?
or A. I don't see a B.
You don't see a b, so what's b?
0.
b is 0.
Plus 3 log natural.
So what's 3 halves? 1.5. So if this is a perfect relationship, or if our data matched absolutely perfectly, what should I have as my linear regression?
Oh wait, never mind.
X.
X.
Plus what's b?
0.
Plus 0. Even if I even choose to write plus 0, this is Kepler's third law. If our data were perfect, how does this compare to how we did? This is with Pluto's data. It's about 1.5, right?
Yeah.
It's about plus 0.
Yeah.
It's a little off from that. This is without This is even better data excluding Pluto. This is this is this is even closer to 1.5 and even closer to 0.
Oh.
That's the meaning behind my line of best fit. That's why on my graph I had a slope. What was my slope on my graph? What's my slope of this line?
At that 1.5.
It's 1.5. That means the vertical data has a cube relationship and the horizontal data has a squared relationship. 3 divided by 2 gives you 1.5.